So there are like a lot of build tools now. And I guess you need something to stand out, right? So maybe the perfect one. Who am I? Well, that's me. I'm Steve Vogt on Twitter and GitHub. I work on CBT. I'm partly responsible for Slick and used to be in Martin's lab, and now I'm a software engineer at Symbiont. So what's this talk really about, just to give you the right mindset for what's to come? And well, we're going to solve a series of tasks first. And basically, these tasks require to build code. And in order to do that, we'll just create our own little build tool. And we'll apply minimalism. So basically, in order to achieve the tasks, what's the minimal things we can add to make it happen? Not necessarily what's the quickest to do, more like what's the smallest thing. And it's really to take small, conscious, and well understood steps. Because if you just bring in the first best thing that solves your problem, this may bring in a lot of other things as well, which then cause new problems. So by taking small steps, and I like this in software development in general, you move forward in a very controlled way. And then we'll discuss design choices and going further than what we do, talk about what design choices other tools have made and what the impact of those may be. And disclaimer, this is like not a talk that tries to be comprehensive or describe everything. I focus on a few things that matter to me, and there may be other things that I don't even know about other tools implement or solve in some way. Well, this clicker is not. Let's see. Okay, why make this talk? Well, there are a lot of design decisions that went into build tools, and some of them only become apparent when you start writing one of your own. And really understanding these design decisions allows you to understand the trade-offs, and understanding the trade-offs makes it easier to choose what you really want, or makes at least the choice more informed. Because you will have to use some tool, right? So understanding design choices, understanding the trade-off. Okay, let's start with the first task. Compile and run something. So what do we need? Well, we need a computer with an operating system, and we need some Scala code to run. And we probably need a JVM to run this code on. And we need Scala to compile the code and to have a library that runs it. And we somehow need to invoke this stuff. So we may wire it up. Maybe for starters, let's just use bash to invoke Scala. So so we have a main Scala, and we can say Scala C main.scala. And let's say we do target directory target. So now we compile this file, and the file doesn't contain anything too interesting, just a little hello world. And then we can run it, right? -cp target main. Okay, that's simple enough. And if we want to keep doing this over and over, we might as well put this into a little file and maybe add some other stuff as well. So there's a simple way to just build a very simple program, right? Okay, so we have that figured out. Let's do something more interesting. Let's add dependencies. And even for dependencies, since Corsair, there's like a simple solution available that you could just use from bash, so it doesn't get much more complicated, right? We can just add it to our script as well. We can call Corsair, and we can call Corsair on some library. So let's say Corsair fetch Scala test, and we'll get a class path where this is available. And then we can just we use ScalaC to compile our main code, and then we use ScalaC again to compile the tests, referencing that class path, and then we can invoke it. So we did a lot of what you would do with the build tool, just with a few lines of bash code. So what about these other things? Packaging your code, signing it, publishing it to Sonatype or something like that. Well, you can call the jar command line tool to wrap up the class files. You can call GPG to sign it from the command line as well. You can use CURL to upload it to Sonatype, or there are even command line clients for Sonatype. And still, it's like just a very small step to still do this in bash. And now you might ask, okay, we have it all in one script, so it like all runs one after the other. What if you kind of want to invoke tasks separately? So of course we could go ahead and split up the script. So here I have another project where there is the script compile, which does most of, like some of what the script we've seen just a second ago does, but it only compiles, and then we have run, which calls compile, and then runs the project. So if we go into do.compile, so I configured the bash script to give a bunch of meta information. We saw it compiled, and then if we run, we can also run it or test. So even breaking it up into separate tasks is not too hard with bash, right? So maybe bash is the perfect build tool. It was very easy to get these things done, right? The end. Or maybe not. Okay, so let's take a deeper look. Why aren't we using bash for builds? It was really quick to do, right? And this may be harder to answer than you might think, because process calls are really simple. Usually processes have very simple interfaces to call, and there are actually many helpers available, some of which I didn't really know before I prepared this talk. For example, there are a bunch of flags you can give to bash, which makes bash scripts a lot safer. Pipe fail and a bunch of other parameters that, yeah. And then there is shell check, which is a linter. Like both these flags and shell check is something I use a lot now whenever I have to write a bash script, which I try to minimize, but it does help when you have to. And then there are command line clients for most things you might need. There's even a bash debugger, which I didn't know about. And maybe one of the main reasons why we're not using bash, I mean, there are several, but maybe one of the main ones is really dependency resolution, because sure, we used to use bash and make and these things for building programs, but then the internet happened and everything got distributed in lots of different operating systems. But the problem is these command line tools you have installed, they're usually somewhat installed in a platform-dependent way. You installed them, I don't know, with apt or with pacman or with homebrew or with just calling installers. So that's hard to replicate reliably on different developer machines and on the continuous integration system or in the production system. So there's fragility. And then one of the big things that Java and Maven brought to the table is this platform-independent dependency resolver that just works. And maybe that's the reason why build tools are successful relying on the JVM or also relying on Python, because it's just cross-platform, so it's easy to get to work reliably. However, with the advent of Docker and VMs, you actually kind of have a mapping layer to go back to make bash cross-platform too, because you just map to Linux within your whatever operating system. So, I don't know, maybe bash and Docker is actually quite viable. But we probably want to do or can do better. And so let's look at some of the decisions that tools have made and what the impact of these might be. And let's build a little bit of a mental framework in order to compare this. To just not, to try to be less just judgmental, but try to break it down a little bit, even though it's hard. And two keywords I like to think about generally in software development is effectiveness and efficiency. Effectiveness is basically does it get the job done? And efficiency is how well does it get the job done? So basically, you want to achieve effectiveness and maintain it. You don't want to lose it, and you want to optimize efficiency as much as possible. And in a way, when it comes to build tools, that's productivity and risk. Like, so how productive you are with the tool in developing software is how efficient the tool is. And obviously, it has to be effective at building things. But effective is not just black and white. There's a risk involved. If for some reason your tool stops working, you lose effectiveness, or maybe efficiency in terms of it's like getting slower or something. So you need to manage that risk. And things are connected. So if you optimize like one aspect, like maybe reduce the risk of effectiveness, maybe that reduces usability. Or if you improve performance, take some shortcuts, maybe you have a higher risk of breaking. And also requirements differ for everyone. So there's this whole like large web of like different things that people care about, and they're kind of all interconnected. I don't know, ease of learning, parallelization, caching, productivity, access to experts, and every design choice we make affects one of these things, and sometimes several. One of my favorite ones actually is extensibility, because at first sight, extensibility, like adding your own functionality to a program, is such something that allows you to build new things. But in a way, if extensibility is easy enough, it can also be something that increases ease of use, because it may actually be easier to build something from scratch to solve your problem rather than learning how to use the existing solution of someone else. So extensibility is something that I personally find very important. But there are all these different aspects, and we'll look at a few design decisions now and see maybe how they affect some of them. So, and focusing on these individual aspects is obviously easier than saying, oh, this is just better, or this is more productive. So one design decision that a lot of tools have made is use a different language than Bash. That's very simple to describe. So what's the impact? So I don't know, one impact, maybe it's less simple, or maybe not. This is probably the broadest, like the least easy to grasp design decision. But maybe ease of use or debuggability get better, or reduced risk, because you're not relying on having the right tools installed in your system, but using a dependency resolver that installs the right versions of things or pulls them. Okay, so that's a somewhat of a vague design decision. And I guess it has a lot to do with who your audience is, because familiarity with the technology can affect ease of use. And obviously familiarity is very subjective. So let's look at something more concrete. Earlier when we just invoked Scala from the command line, we saw that invoking the Scala compiler here took about 5 seconds, or invoking just running the code took like about 1 second, and that's quite the overhead. So tools have come up with different mechanisms to avoid this overhead. Basically improve performance, right? Make our tool more efficient. And what SBT did is it has a shell. So you call SBT, then it takes a little moment, but now afterwards, whenever you type a command, it's very quick. It just keeps the process running. So what's the impact of this design decision? Well, obviously performance increased, the turnaround time, but also you do lose the access to bash features which you usually have in a command line. So maybe because you can't wire it together with grep and these tools, extensibility decreased, right? And maybe ease of learning decreased as well, because this shell works differently than the shell that you usually use. and thereby ease of use could reduce too. And there's a different design decision that other tools have taken, CBT or mill, I think Bloop as well, which is have a background process running. For example, using Nailgun, which helps doing that. Which now you just call things from the command line, like let's exit this. You just do CBT, I don't know, run or test, and you can grab for an error. So you don't lose the extensibility, you don't lose the usability of your ordinary shell, but this decision is also one that it's also a trade-off. It's not purely only beneficial because having this process running in the background is a side effect, and sometimes it can be surprising. Sometimes like the behavior changes depending if the process is up or not. Maybe there's a bug that affects the process in the background. So it's also something that can lead to problems. Okay, so these were so far pretty smallish features. Let's get to some more interesting things. Project graph reification. So basically the build tool having understanding of what the projects are you have in the build tool and how they relate to each other, how they relate to dependencies. And that's actually something that all the build tools do. The reason I put it here is to compare it to a few other things. So all the projects build this graph somehow, except for maybe this old Unix tool redo just traverses the graph, or maybe make, but most tools do this, especially in the Scala world. Another thing that some tools do, and I think when it comes to Scala build tools, all tools except for CBT, is they reify the task graph. So within a project, you have different things to do. Download the dependencies, maybe generate some code, maybe compile code, but for that you need the code to be generated and you need the dependency to compile it against, and then run the compiled code. And there's an order to these things. And most build tools, they want to understand this graph. And this requires usually a two-step process where the first step is you run through configuration files or code or some monadic structure or something to basically build this graph. And then as a second pass, you execute this graph. Maybe all of it, maybe just a part of it, depending on your analysis. And there are promised benefits of this reification. The tool knows the graph, so it can give you mechanisms to inspect the graph, right? To say, oh, what are the tasks available, or which tasks depend on which other tasks. You can do static analysis. You can, I don't know, detect cycles in the task graph, which may be a problem. Or you can potentially, when you realize something changed, you can only rerun part of the graph. Bazel does that in a very impressive way, where it keeps the process running, monitors file changes in the file system, and when something changes, just recomputes, basically rebuilds the subgraph. So in a way, it also contributes to having reproducible builds. Might also give better error messages. So the promises are better ease of use and better performance. But there's also a different way to look at it, because it comes at a cost. And this is a cost to be aware of. So this task graph reification and the evaluation of the task graph, it's evaluating computations in a certain way. And you probably can use your ordinary Java debugger, which you may, or tracer or profiler that you use every day for analyzing what your build tool does. So you need to use, I mean, if the build tool even offers this functionality, you need to learn the functionality of the build tool in order to do these tasks on the computation graph of the build tool. And this is learning that's specific to your build tool, because usually these task graph evaluation systems, they're specific to the one tool. That's not a general thing that you use for other problems as well. They're build tool specific. And then in order to build this graph in the first place, the tools usually have some kind of UI or API, and that's usually not that easy. If you look at, for example, here's Mill's description. There are targets and sources and commands, and then you have to wrap the code you put into tasks in these scopes and the ways to refer to other. So you have to basically, in order to use mill, maybe it's not that much to learn, but it is something you have to look at and understand how to use and keep in mind. And I haven't used mill, so maybe this works really well in practice. Maybe this is a very worthy investment. So I don't want to make a judgment on that. But it is an investment that you have to make. And similarly in SPT, you have to learn what this dot value means, and you have to learn how to define tasks and how to reference tasks in other places. So all of these are operations that are basically telling the build tool about this graph. And then the execution model is also one that is specific to this task. That, I mean, I think in mill and in SPT, it's an applicative model where all the references you have are always evaluated up front, even if they're inside of then or if, like then or else statements or something. And then the place in your graph is evaluated. That is necessary in order to have a simple static analysis over the task graph up front, but it also is a different semantic execution model than ordinary Scala code, where references work differently. They're only evaluated conditionally. And in a way, we know that SPT is particularly complicated when it comes to this graph with all these concepts like names and axes and scopes and the lookup order of keys in certain axes or scopes. So there's quite a cost to this. And build tools are a narrow use case. So you pay this cost for only the build tool usually. And it's also something that, depending on your project, you may not touch every day. So it's kind of hard, like it's even hard to retain this memory of how to operate this graph. So the more complex it is, the harder it gets. And is this even necessary? Maybe, maybe not. At least from building a build tool myself, I've not been necessarily convinced that it's necessary. I'm not saying there aren't good reasons to do it in the end that I may not have fully understood yet, but to me it seems more like within a single project, you usually invoke some task and then the dependencies are somewhat linear. There's very little splitting. Maybe the compile step needs code generation and dependency resolution, but then if you run your tests, you need to compile and maybe do these two things. And so instead of having your build tool understand this graph, you could just use Scala's execution model. You could just really have methods calling each other, and then you get all the introspection and analysis feature that Scala, your language, offers. And unlike other languages, Scala has a lot to offer there. So yeah, basically, instead of doing something dot value where then the build tool understands, oh, the run task refers to the compile task, and now later there's an evaluator running. If the compile task is a method if the run task is a method that's calling the compile method, then it's the JVM responsible for this. And if something goes wrong and you get a stack trace, the stack trace will reflect your tasks. And the type system can help you reason about the task graph because it's just the method call stack. And you can use your profiler and your tracer. And you often lose this when you have a process where the building of the task graph is a separate step from the evaluation of the task graph. Because if you only build the task graph in the beginning and then have a data structure that's evaluated, the stack traces and these things, they don't make sense anymore when they happen in the evaluator. And in a way, you can still get a lot of the things that other build tools do, that build tools do with the task graph without having this task graph at hand. For example, in CBT, there is this memorize function which is offered as part of CBT's library, which people can use to wrap their task to memorize the result. And you can equally have things like this for logging or other effects that may give you information about your task graph. You can't get it ahead of time, you get it during runtime, but then you have the type system to do ahead of time analysis, and these things to do runtime additional analysis to what Scala or the JVM already offer you out of the box. And maybe something that having the task graph in the build tool is that it gives you additional power to enforce these things happening. On the other hand, you can think about it differently. Making it easy to do the right thing, but not forcing is also a mechanism. And yes, this task graph is often used for incrementally re-executing part of your entire large graph of things that need to be done. But is the project graph maybe enough for this? Because all the build tools, including CBT, they reify the project graph. Even if you have if you have Twitter or a company with 50,000 projects, is it maybe enough to just recompute part of the project graph, but basically run through all the tasks in this subgraph and have each of the individual task steps that is invoked be responsible for potentially doing nothing if nothing's necessary? So in a way, my point is, this is a very costly step in terms of usability and in terms of weight of the tool. And it's a heavy trade-off to make if it's necessary or not. So another thing that SBT does, and I think Maven as well, and a few tools, is that Stack in Haskell land as well, where it somehow distinguishes different types of projects or packages. Like SBT calls them configurations. So in project A here in this example, you have the main code and you have the test code depending on the main code. An alternative, what CBT does, is that everything's just projects depending on each other. And there are some advantages and disadvantages to that. The advantage is the model is simpler. There's only one concept of things that can depend on each other. So you interact with all of them the same way. You also get all the features immediately. You can depend on any of them. You can have a dependency on your test sources. In other tools that have a different concept for these subparts, now you need to invent a language to operate with this other concept. In SBT, you have to specify, oh, normally I depend on the module, which kind of implies you depend on the main configuration. But then if you want to do something else, you have to use like the percent test operator to refer to it. But you only need this language because the concepts are made different. On the other hand, by making them different, you might be able to give better error messages or something like that. But my feeling is that this trade-off in terms of the special casing is probably not worth it, because probably the value you get out of it is smaller than the complexity that it causes. This is an interesting one, and I think one that's often overlooked. I call it like framework-style code reuse. So ultimately, a build tool allows you to do multiple things: compile things, test things, run things. So in a way, there are multiple entry points into your logic, multiple things you can do. And those things somehow interact with custom code you've added, build description or something as well. So you have to understand how your usage of the tool from the command line or the shell or something maps to how the tool interacts with your own code. And there are different ways to do this. And in a way, all build tools in the Scala world, they do this framework-style code reuse. But what we did with our little bash experiments a second ago, the entry points were very, very clear, right? So here in this example, we had the script compile. So you call this script, you know what invoking a bash script does. It starts at the first line and goes through. Or you call run, and you see, oh, you go to compile here. So you know the exact entry point, you can follow every single step of the way. And we could do the same with the build script written in Scala. So this is like an analogous thing written in Scala where you have a bunch of these objects, each of them with a main method, and you could say the way my hypothetical build tool works is people have to put those into their build description. It's very explicit. It's really now you start using the tool as a library, not as a framework where the framework would call you. Here, you know the exact entry points. And I know that there's some people in the community that would like to use build tools this way, where it's very clear. And you could say, okay, the only thing this does is invoke these things. And maybe this is a little library or little build stuff you wrote for your own build tool where you explicitly make all these calls. And then this is provided by your build tool, which is the actual functions that do compilation and stuff like this. But then obviously this would mean you would have to repeat all of this for every build description. So it's an obvious thing to think, okay, let's avoid this boilerplate. Let's reuse this, let's abstract it away. And then you would end up with something like this, where, maybe there's a main method in your build tool itself. So this is provided by the build tool. And then you do something maybe, I don't know, you look up the class build, and then you use the first argument of the command line to invoke some function on this, which is roughly what I think CBT and MIL are doing. But you did take away the entry point from the stuff that's immediately visible to the user of the tool and put it into the build tool itself. And then now you added required knowledge to the user. Maybe that's worth it here, especially if you try to keep it simple enough, but it's the thing, you only come back to your build tool so often, and so it's the harder this mapping is, the harder it is to remember. Right, so yeah, CBT and MIL do very simple like command equals method. And in a way, I think one point is that more reuse doesn't always mean it's more efficient for whatever metric of efficient you have in the moment. And as we defined efficiency of a build tool in terms of productivity of the user, if you forgot how things work, maybe it would have been more efficient for you to have them basically replicated in your thing you work with. So having code duplication is not always something that makes you less productive, sometimes makes you more productive. So in a way, I think there's a little bit of an unclaimed spot in the market where, especially probably some of the more pure functional programmers in the community would like to have a tool that's really more like a library that you use from a custom script rather than a framework that kind of controls how you do things. That's an interesting one. So one thing that build tools pick up more and more is this concept of reproducibility. And I think this is mainly about reducing the risk of losing effectiveness. So reducing the risk that it doesn't do the job anymore. But I think it probably also improves ease of use, because if you reduce the risk of something going wrong, then yeah, there are fewer obstacles. And I think, yeah, especially that's something where the build tool movement seems to be shifting. I think MIL focuses on this, and Bazel focuses on this, and I think the tools by Twitter and Stripe do as well. Oh yeah, and something very interesting, like a very interesting feature in Bazel, and maybe some of the other tools, is that in order to achieve reproducibility, it sandboxes certain parts of the computation. So let's say your compiled step is actually run in an isolated sandbox in the system that can only affect the things that it actually needs access to, which I think is a little bit of a game changer, because a lot of what build tools do is highly side effective and highly changing things on disk. So also risky if something goes wrong. Like You may delete the wrong folder if there's a bug in the tool. And especially if people are encouraged to add to the build tool and extend it, or add to the build descriptions, this isolation is something that's maybe a really nice step, a thing to do and add for more build tools. Here's one thing that's very important for me personally, and I think that's also often overlooked. We have a little bit of the problem in, I guess, think in the programming language or in the software development community in general. There are all these ideas and lots of volunteers and lots of work being done and lots of great projects, but often the number of people who can work on them is very limited to a small core. And some of it is because some problems are hard, like working on the Scala compiler can only get that easy. But that also means ideally you should take away all the hurdles that can be taken away to really reduce it to only the challenges that are just intrinsic to the problem. And right now I think library development and tool development becomes unnecessarily hard because, okay, so you download the tool, you install it maybe through your package manager, but now you want to make a change, and in order to do this you have to find out where the sources are, probably on GitHub, you have to clone them, you have to build it locally, you have to figure out how to do this because they all have a different build, and then you have to start running it, and that's basically the entry point for somebody who wants to just use it and the entry point for somebody who wants to make changes to it are very different. And often enough, I think people are just making either a local change or like, whatever, I don't bother, like, or write some script surrounding it that makes the change they need, rather than changing the tool for the better of everyone. So I think one thing that build tools really can change, but also that should be changed for build tools, is making it easier to contribute. And one design decision that CVT made in order to do this, but it's something that I think can be replicated to at least other build tools, but probably any other tools and potentially libraries, is that CVT bootstraps from source. The only way to install CVT is you clone the source code and you run the launcher. And it's exactly the same if you want to change CVT or if you want to just use it. And referring back to the talk, to John's talk this morning, I think there's a big missed opportunity to do things from source and in a way that makes it easy to change. So for the build tools can support more, or can have better support for source dependency of libraries, so software developers can change the libraries they're using more easily, but then tools themselves can also start having launchers that make it very easy to make changes to the tools themselves. And I think one thing that became apparent to me again, and I don't know who was in the SPT talk yesterday, but at some point there was a description of things evolving in the ecosystem surrounding SPT, and when they become like stable enough or good enough, they merged back into the mothership. And in a way, that's a little bit of the problem, of a problem that our build tools have right now. They're these huge monolithic things. And I think we should do more. And there's effort going on, but we should really double down on the effort of breaking it up and making things available separately. And CVT is no different there than the other tools, that these features are somewhat bundled. And I would really like to progress in pulling things out, maybe making the from source launching part separately available so we can use it with Bloop or with other things as well, or the part that keeps the process running in the background. I think that's something we should push for, isolate these things out so they're more reusable and can be more combined. So concluding, it's all about trade-offs, and it really depends on you what the right trade-off for you is, and I hope we make it easier to choose one thing without having to choose everything else as well. And it's hard to make very clear judgment about what's better because things are very highly connected. And in a way, understanding the design decisions better, I think, allows you to make better choices and get less frustrated when things don't exactly work the way you think they should or you want them in the moment. And that's where I work. We're hiring. If you want to work on a cryptographic log database, aka blockchain, do some advanced functional programming, work with distributed systems, cryptography, programming language design, talk to me. Yeah, that was my little adventure through build tool design decisions. Thank you.
Okay, maybe one question, one short question. No? Yes, it is one.
Short question, any ideas on quick comparison with Gradle?
I don't know Gradle very well at all. So, yeah, that's the answer. I think he wants to follow up. Okay.
Gradle basically does build description in Groovy. So you write a Groovy program that actually has some things you can call like to the external world, and then you write your build as a Groovy program, basically.
Yeah. So I guess my take on this whole thing is programming languages are great to write programs. And I choose languages that help me do this in the best possible way, give me the predictability and the introspection capabilities that make it easy for me to write programs. In a way, the same thing applies to builds as well, because a build can be seen as a program that builds your real program. So basically, by delegating as much work as possible to the programming language and the compiler and these things, rather than the build tool itself, I personally find I benefit because I can reuse that knowledge. So I really like using Scala for my builds rather than Groovy. Okay, thanks so much.